Good evening. Today I'll be covering a normally distributed random variable such that the parameters depend on a Bernoulli random variable. And then we will be deriving two statistics. One is the expected value of that new dependent random variable, and then the standard deviation. And so this will kind of showcase how does a continuous random variable mix with a discrete random variable. And so I'm first going to start off by defining the density of the parameter. So here I'm using theta as an arbitrary parameter, and like I mentioned, theta will take on a Bernoulli distribution with a success probability of 0.3. So we'll just say 0.3y 1 minus 0.3, which is 0.7, 1 minus y, where of course y takes on values 0 and 1. So if y is 0, then it's 0.7, and then if y is 1, then it's 0.3. So then now let's define our dependent random variable x given theta. And I'm going to write this in a somewhat weird way, but it will make sense shortly after. So I mentioned that this is a normal random variable, and for the variance, I'm going to denote it, let's say p0 square root 2 pi. Try to ignore my bad handwriting. E to the negative 1 over 2 p0, which is our variance again, squared. And then we have x minus p1, which represents our mean, squared. Okay, so this looks like a normal random variable besides these weird p0 and p1 things. But these p0 and p1 things are actually depending on the values of our parameter p theta, because this is a dependent random variable. So for the mean, I'm going to define p1 as 3 if our Bernoulli random variable equals 0. Let me check. I have this simulation here as an example. So I have 3 when b equals 0, our Bernoulli random variable, and then 5 otherwise, or when it equals 1. So we got 5 for p of 1. And this is actually p of, it's supposed to be p of y, but that's okay. Yeah, I guess I should, for this to make a bit more sense, this should actually be, we'll set this theta to be theta. So theta in this case is our discrete portion, and then our value of the Bernoulli parameter is 0.3. So hopefully that's not confusing. Now theta is our 0 or 1. So at p0, when our Bernoulli random variable is equal to 0, then our mean, p1, is equal to 3. And when our Bernoulli random variable equals 1, then our mean equals 5. And so let me take a step back and kind of explain intuitively kind of what this visually looks like. So imagine that you're flipping a coin, and in this case it's not a fair coin, we land on heads 30% of the time. And depending on the face of the coin that you land on, you generate a normal random variable from a different distribution. Let me actually finish P0 and then I'll kind of finish that analogy. So for P0, I defined, let me take a look again, standard deviation of 2 when it's 0 and 1 otherwise. So 2 P0, 1 for P1, P of 1. Okay, so I flip a coin. Flip a coin. My handwriting is terrible, but that's okay. And if I land on heads, then I generate a normal random variable with mean 5, variance 1. If I land on tails, however, then I generate a different normal distribution, or normal random variable, with mean 3, standard deviation 2. And so what scenario would you run into this? I'm not sure, since this whole video is a toy example of mixing continuous and discrete random variables, but this is one way where you can think about this type of situation. Okay, so moving on, let me quickly erase these things. Kind of just messed this up. Okay, so now that I have my mean and my variance defined, how do I actually get my density of x? Well, as you might know from conditional probability, and something that I've covered before, if we want the marginal distribution p of x, then essentially we need to evaluate, in the general case, I'll use an integral, we need to evaluate our dependency joint with our dependent portion and our, I wouldn't say independent portion, but the parameter with respect to the parameter. So in general, this is typically how you will see marginal probability. However, note that d theta is discrete, not continuous. And so instead of integrating, which this would probably be a bit of a nightmare to integrate, this will actually be a summation. We will be summing over the values of theta, which is 0, 1. And we will be summing p of x given theta times p of theta. So this is p of x given 0 times p of 0 plus p of x given 1 times p of 1. So expanding this out a little further, so p of x given 0, what is this? So we take this, and now we have theta equals 0. And so our standard deviation, when theta is equal to 0, our variance is 2. So this is 1 over 2 root 2 pi e to the negative 1 over 2 times 2 squared x minus, and then our mean, when theta equals 0, our mean is 3. So this is x minus 3 squared plus, and then we do the exact same thing for this one. So now theta equals 1. When theta equals 1, our variance is equal to 1. So this is just 1 over root pi, or root 2 pi, excuse me, e to the negative 1/2 x minus, and then for our mean, when theta equals 1, our mean is now 5. So this is our marginal density for x. This is the actual density of our new random variable. And I'm not going to plot this, but if you were to plot this function here, you would get something that looks kind of like this. Usually this is referred to as a mixture distribution, where this is now this is a bimodal distribution controlled by this discrete variable here. And as you can imagine, if we had a multinomial distribution, then we would have a multimodal distribution. But here we're just dealing with the binary case, a Bernoulli distribution, so this is bimodal. Okay, so we derived the density of our new random variable, and I accidentally eradicated this variance here. So we got 2 questions, which I've already hit the 11-minute mark, which is crazy because it doesn't feel like it's been that long. Time flies when you're having fun, I guess. So the first question I want to answer, actually before that, I'm going to rewrite this in a much more clean and readable way. So, something I totally forgot. These are the normal distributions that we just did. But what I forgot to do was the actual discrete portion, which is actually very easy. And this is also supposed to say 0 and not theta. My bad. 0. Okay. So, I'm not sure if I can move this. Let me see real quick. Okay. Alright, I can move it, that's good. I made a slight mistake. Okay. So we did the conditional pieces here, but what we forgot to do is these pieces. So what is p of 0? We kind of already mentioned p of 0 is 0.7. Get this pen. 0.7 times this whole nonsense. And then when theta equals 1, this is 0.3, which is our success probability. Okay. So now, after mistakes corrected, I'm going to rewrite this in a slightly cleaner way. P of x equals 0.7, and this is just a regular normal distribution. So I'm just going to write n, the normal distribution notation, and this is a normal distribution with mean 3, standard deviation 2, plus 0.3 times normal distribution of mean 5, unit variance. So I think this is a bit more readable, and we can go on with this. So let me clear up everything here, because I'm assuming that you understand up to this point, because I am running out of room on my whiteboard. And we're going to take this back up to the top. And now my whiteboard is lagging extremely hard for some reason. Okay. There we go. So now there are 2 main questions I want to answer here. First question, what's the expected value of x? And then second question, what's my standard deviation of x? So one of these is much easier to answer than the others, and that's this one right here. So let's go ahead and answer this first. So to take the expected value, recall now that x is actually a continuous random variable now because it's a normal distribution. So unfortunately, we can't simplify this into a discrete way using a summation. And so the expected value, I'm going to go over here. The expected value, whoops, will be equal to the integral of x px. You should be familiar with this if you study probability or statistics in general. And so this is equal to 0.7, or the integral of 0.7 n 32 times x plus, due to linearity, the integral of 0.3 n 51 x, and of course this is with respect to x, but I was kind of lazy and didn't write it. This is with respect to x, and of course we can take out the constants here. So we got the integral of 0.7 times x times the normal distribution 32 plus 0.3 times the integral x normal distribution 51. So notice that these integrals are just the expected values of these normal distributions, which is very easy because the expected value of a normal distribution is just the mean here. So really what this boils down to is 0.7 times the expected value of this normal distribution plus 0.3 times the expected value of this normal distribution, which finally boils down to 0.7 times 3 plus 0.3 times 5. And if I pull out a calculator here, this is 0.7 times 3 plus 0.3 times 5. This is 3.6. So 3.6 is our expected value. Alright, so now the more complicated one, which is variance, and this one is a little bit more involved, but it's not terrible. So I was actually going to do this in a much more complicated way, but after doing some thinking, we can probably utilize the shortcut for variance. So one common formula for variance is the second moment minus the square of the expected value. And we can probably utilize this. What I was going to do is I was going to take the actual direct computation. So using the expected value that we just did, I was going to do this integral, which is possible, and it's actually the way I did it off camera before recording this. But after doing some thinking, we should be able to use this and not this, which takes a bit of time. So let's go ahead and try. I didn't actually try off camera, so this will be kind of bad if it fails, but let's directly attempt it. So utilizing a similar approach that we just did before, we could do 0.7, I'm going to take the constants out, times x squared normal distribution of 3, 2, dx, oh, I won't forget dx this time, plus 0.3 times the integral x squared, normal distribution of 5, 1 dx. And so just like before, now we can look at the second moment of these normal distributions, and the second moment is sigma squared plus mu squared. So if we apply that, then we get, let me move this over a little bit, make this clear on what exactly I'm computing. Right now we're focusing on the second moment of x. Okay, so this is 0.7 times, well, sigma squared, which is 4, plus mu squared, which is 9, plus 0.3 times sigma squared plus mu squared. And then we have all of this. Oh, actually, I'll leave it there for now. So let me get out the calculator again. So this is 0.7 times 13. I didn't actually need brackets there, but whatever. Plus 0.3 times 26. So this is 16.9. And so now, computing the variance, we can use the second moment minus the square of the expectation. And so this is 16.9 minus 3.6 squared, which is 16.9 minus 3.6 squared. This is 3.94. And then, of course, the standard deviation is just the square root, which is 1.985. I'll round it. Okay. So this is the correct answer because I've already simulated this off camera. But I'm actually glad I thought of this approach because that was much quicker than doing it the very long and tedious manual way of computing this integral, which again is kind of time consuming. But now that we have the values that we were expecting, specifically these ones right here, let's actually head over to our studio, which I pulled up earlier in the video, and then we'll actually simulate this. So before I run it, I'll kind of show you what's going on here. So I have this variable b, which is a Bernoulli random variable. I'm pulling one random variable, and this just goes from 0 to 1, and with a 30% success probability. And then if b equals 0, we pull a random normal variable with mean 3, standard deviation 2, and then if b equals 1, or in our derivation if theta equals 1, then we pull a different normal random variable with mean 5 and standard deviation 1. And then we compute the mean and standard deviation, these two statistics that we just computed. So we should expect around 3.6 and 1.985. So and I'm running this for 100,000 simulations. That should be plenty. So let's go ahead and run that. And now the mean, we got 3.600669, which is in line with what we're expecting. And then the standard deviation is 1.986914. So, looks like the simulation lines up with the statistics that we computed by hand. That's good news. And that's pretty much how you can mix discrete and continuous random variables together. Hopefully you learned something new. This video was actually way longer than I was expecting, so apologies. If you made it to the end, then I owe you a cookie or something. But yeah, that's about all I have for now. Thanks for watching.